Introduction. In fluid dynamics, a hydraulic jump is a phenomenon that occurs when a fast-moving fluid traveling over a surface suddenly decelerates. The sudden loss of speed causes the fluid's height to increase significantly. The sudden transition burns off a massive amount of kinetic energy and creates heavy turbulence. You will typically spot this happening around dam spillways, open channel, and similar waterwork. For hydraulic engineers, anticipating the exact location and the size of this jump is a critical part of the job, mainly because they heavily influence both of the structure design and the overall safety of the system. Next is objective. The objective of this experiment is to study characteristics and behavior of hydraulic jump, such as its location, size, and energy dissipation. Next, applying this finding to forecast the reliability of canals, dams, and spillways that help improve structural design and guarantees that the final birds are both safe and highly efficient.
What is hydraulic jump? A phenomenon where a high velocity, shallow liquid flow, supercritical, abruptly transition into a lower velocity, deeper flow, subcritical. It results in a sudden rise in the water surface accompanied by violent turbulence. The core purposes and uses for hydraulic jump is energy dissipation. Destroy excess kinetic energy in the water to prevent erosion and damage to structures like dams and spillway. Chemical mixing. The intense turbulence is highly effective for mixing chemical in water treatment plants. Flow measurement helps in the measuring the discharge rate of an open channel.
Okay, first step to conduct this experiment is we must measure the width of the rectangular upper channel. So the width rectangular of upper channel is 7.7 cm.
Okay, first we measure the height of the sluice gate and the opening is 10 mm. After that we tighten the sluice gate so that the water don't push it.
So next we turn on the hydraulic bench and then open the valve to control the flow rate. The dump valve, so the water tank is fitted. And then we measure the flow rate by fixing the volume and set height. The next step is we put the gate to treat the hydraulic jump. So for the next step, we measure the height of the downstream using this point gauge, and we measure the upstream using the same point gauge. Upstream height, and we record the data.
We move on to the next part, result analysis. As you can see in the table, this is the data that we got from our experiment. We find the height of the tailgate, height of the sluice gate, volume, time, subcritical depth D, supercritical depth D1, subcritical depth D2 after the sluice gate, and distance hydraulic jump from the gate. By using the data, we calculate for the discharge, velocity, Froude number, head loss, and power loss. For our sample calculation, we use 0.01 height of the tailgate. First, we'll calculate for the discharge using formula discharge equal to volume divided by time, and then we get our discharge Q equal to 0.00123 meter cube per second. Continue. Second, calculate for the velocity V1 and V2 using formula discharge equal to area times with velocity, and we get our V1 1.33 meter per second and V2 0.29 meter per second. Third, calculate Froude number 1 and 2 using formula Froude number equal to velocity divided by square root gravity times with depth, and we get Froude number 1 3.88 and Froude number 2 0.39. Fourth, calculate head loss using formula head loss equal to D2 minus D1 in bracket of 3 divided by 4 times D1 and D2, and we got 0.032 meter. Fifth, calculate power loss using formula power equal to density water times gravity times discharge times head loss, and we got 0.3825 watt. Lastly, check for the hydraulic jump is generated or not by referring to the Froude number. Then we summarize all of it into a table here.
For the discussion, the Froude number is an important dimensionless parameter used to describe flow characteristic in open channel by relating the flow velocity to the water depth. In this experiment, the hydraulic jump was stimulated by varying the sluice gate opening of 0.01 meter, 0.15 meter, and 0.2 meter under one different discharge rates, which is the Q. The experimental results show that at a constant discharge, the upstream conjugate depth decreases as the downstream conjugate depth increases. This behavior indicates the formation and the development of the hydraulic jump. Furthermore, the upstream Froude number increased as the upstream water depth decreased because a shallower flow resulted in a higher flow velocity. Similarly, increasing the discharge at a constant upstream depth also led to a higher upstream Froude number, as the increase in flow rate produced a corresponding increase in flow velocity. These observations are consistent with the theoretical relationship between the Froude number, flow velocity, and water depth in open channel flow.
In conclusion, this hydraulic lab session successfully evaluated the relationship between flow rate, velocity, and hydraulic structure. The result confirmed that proper channel dimension and pressure management are vital to optimizing fluid flow and preventing energy losses, providing essential data for practical hydraulic engineering design.